Okay, students, to build on what we had discussed last time, I just want to bring back in a couple objects that we saw. So we noticed that with infinite series, we've got a pretty good grasp on how to determine whether such things converge or diverge. Should the terms of the series not go to zero, should the terms limit to something other than zero, we know that such a series diverges. We've also seen with geometric series, in fact, precisely when those converge and precisely when those diverge. In fact, we know more. We know precisely what the series converges to in terms of its value. That's a really powerful thing. We know exactly what the sum is in those cases. And we've also looked at telescoping series. So this gives us a grip on some of our infinite series. And if I may, to bring a slide that we sort of discussed previously. When talking about these infinite series, we mentioned the fact that we like to sort of group these series among the divergent or the convergent. Again, sort of echoing what was on the previous page, if you have a series whose terms tend to a number other than zero, if the limit of the terms is not zero, we know all of those series diverge. So we have the divergence test to provide that. And it was mentioned previously, and sort of I want to come back to this point, that when you have a series whose terms limit to zero, some of those series are among the convergent series, some of those series are among the divergent series. And well, I'd like to make very clear this distinction between the convergent and divergent series whose terms limit to zero. And well, to do that, let me bring an example in. So here's an example of, and I tell you what, let me just do it like this. So here's an example of a geometric series. Now this is, remember what a geometric series looks like. A geometric series is just of the form sum n equals 0 to infinity of c times r to the n. And certainly this is of that form. Here the c is just 1, right? I mean, you could imagine a 1 in there in front of that r that's being raised to the nth power. Here the r is a half. And what we observed with this formula was that should the r be less than 1 in absolute value, you get convergence. And well, in this case, the r is definitely less than 1 in absolute value, because of course a half is less than 1 in absolute value. If you run the series out then, of 1 plus a half plus a fourth plus an eighth and so on, you can see what we get as a result. The result, as it always is just c over 1 minus r when adding up the terms of a geometric series that starts with the n equals 0 term and goes on forever. Well, the c is 1, as we've discussed previously. The r is a half. Work this out. 1 over 1 minus a half, that's 1 over a half. 1 over a half is precisely 2. So why do I bring up this particular series? Because you might say, hey, we just did geometric series a couple videos ago. I want to emphasize the point that this series has terms that limit to 0. Note, the terms 1, a half, a fourth, an eighth, those terms are limiting to 0. And also observe that this series sums to 2. So what we have is a series whose terms limit to 0 and that converges to 2. So in other words, if we go back up to the picture which we have above, this series which we have here falls under the convergent series whose terms limit to 0. Which sort of then begs the question, well, what about this other collection of series? What about the collection of series whose terms limit to 0 but who diverge? Can we get an example of that? And actually, that's the question which I am asking here at the bottom of this page. So can we get an example of a series where the terms limit to 0 but the series diverges? And in fact, we can, and this is a classic example. It's famous enough that it actually has its own name. It's called the Harmonic Series. Harmonic because, well, if you look at harmonic waves, for example, a wave with 1 peak or a wave with 2 peaks or a wave with 3 peaks, for example, these sort of represent in some sense like a whole and a half and a third in terms of their wavelength. So these are sort of all of the harmonics. We're going to add all of these up. So we are going to have a sum from n equals 1 to infinity. This is going to be an infinite series, and it's going to be this sum 1 plus a half plus a third plus a fourth and so on. Now, you have to agree with me here that the terms of our sum go to 0. So if you imagine this, to sort of conceptualize this, imagine you had a pile of trash that you were building. And on day one, you dropped 1 pound of trash into your pile. Your pile has 1 pound of trash. On day two, you come back and add a ½ pound of trash to that. So now, after day two, you have 1.5 pounds of trash. On day three, you bring in 1/3 pound of trash. On day four, 1/4 pound. On day 16, you're bringing in only 1/16 pound. On day 100, you're bringing only 1/100 pound. On day 1,000,000, you're bringing only 1/1,000,000 pound. The amount of trash that's being added to this pile on every given day is approaching zero. The amount of trash that's being added, a trillionth of a pound, is almost nothing. And in fact, the terms of this series then limit to zero. But now the question remains, what is the sum of all of these values? Yes, the terms go to zero, but what is the sum of all of these values? Is it going to be some finite number? Is it going to be some infinite number? Well, to determine what it is, I'm going to use a little bit of a trick here. And what I'm going to do is, instead of adding these numbers up, I'm going to add something that is definitely less than what we have above. So what we have above is whatever it is, and I want to have something that is less than what we have above. So the thing that's going to be less, the thing that the alligator is not going to eat, is going to be what I write out here. I'm going to write out almost the same series, but I'm going to replace some of the terms to make something less. Now, what was replaced? So note, 1/3 was replaced with 1/4. Note that 1/4 is less than 1/3. So, I mean, if we're using this less than sign, I mean, the third is clearly greater, right? Note, 1/5 has been replaced by an 1/8, a 1/6 by an 1/8, a 1/7 by an 1/8. Note, an 1/8 is less than a 1/5, less than a 1/6, less than a 1/7. So this less than sign is working here. And similarly, we took a 9th and a 10th and an 11th all the way to a 15th. We replaced that with a 16th. I mean, a 16th is less than a 9th. A 16th is less than a 10th. So certainly what is down here below is less than what is above. Above is greater, below is lesser. Now, the question is, what does this lesser sum add to? And, you know, why would I even have chosen the numbers that I did whenever I'm writing this out? Well, check it out. So I'm going to put some parentheses around the terms that we've collected that sort of look alike. So if we're adding this up and what this is equal to, we've now got 1, we've got a 1/2, and we've got here 2/4. Now, you might say, okay, what does 2/4 add to? Well, you could write it as 2/4, yes, but that is also a 1/2, if you think about it. And what do we have here in this next parenthesis? Well, this next parenthesis, we took the next 4 numbers and we wrote them all as an 1/8. Well, 4/8 is also a 1/2, isn't it? So we get a 1/2 here as well. Now, you might be noticing a pattern because the last 3 parentheses added up to a 1/2. You might ask then, well, what does that next parenthesis add up to? Because we've got a bunch of 16ths there. Well, how many 16ths do we have there? Well, we've got as many 16ths as we have between 1/9 and 1/16. Well, in particular, I claim there are 8 16ths there, right? The previous parenthesis had 4 things. The previous parenthesis to that had 2. Essentially, there's twice as many things in every parenthesis. And in fact, if you do 16 minus 9 plus 1, you'll get 8. That's the number of objects between a 9th and 16th, if you count them all up. So counting them all up, you have 8 16ths. What is 8 16ths? 8 16ths is also a 1/2. Now, think about this. This sum goes on forever. So, just as we can get the next 8 terms and write them as a 16th, we could go out further and get the next, what would this be? The next 16 terms and write as 1/32. And note, the next 16 terms would be up here as like 1/17 and 1/18, all the way out to 1/32. And note, 1/17 is bigger than 1/32. So if we replaced all of these terms with 1/32, we would have down here something that's lesser. But yet, these 16 terms written as 1/32 do what? They add to a 1/2. And now, what could we next do? Well, because we have infinitely many terms, we could take our next 32 terms and write them as a 64th. Take our next 64 terms after that, write them as a 128th, and so on and so forth. And if we continued this pattern, what we get is 1 plus a half, plus a half, plus a half, and so on. And now we know, though, that whenever you take a half and you add it to itself infinitely many times, there's only one thing you can get. The value here is infinite. So, consider this. This sum of terms, which was lesser than the sum of the terms above, adds to an infinite amount, which means the terms above have to add to an infinite amount as well. I mean, certainly something, if the lesser thing goes to infinity, so too the greater thing goes to infinity as well. And that means then the sum of this harmonic series, the sum of all of the terms 1 over n, has to be infinite as well. So, therefore, the sum n equals 1 to infinity of 1 over n is infinite. And what does that mean? Well, with respect to convergence and divergence, that means this series diverges. And with that being said, what have we landed upon? We've landed upon a series whose terms go to 0. Remember this trash pile we had, where we were adding a pound of trash and a half pound of trash and a third pound of trash and so on? I mean, eventually we were adding like practically no trash, right? Like a trillionth of a pound. But guess what? In spite of the fact that we're adding a very, very small amount of trash to this trash pile on a daily basis, eventually the sum of all of this trash is actually swelling to infinity. And that's interesting. While the terms themselves are getting small in absolute value, the sum of all of the infinitely many terms is going to infinity. So wow, when we look at series, some series whose terms tend to 0 converge to a finite value. Other series, if I may, other series whose terms tend to 0 add to an infinite value and diverge. So what we've done is we've now found from series who tend to 0, we found a series that converges, that geometric series example that we worked, and we found a series that diverges, the harmonic series.